This lesson is about graph isomorphism. So we're going to be talking about what isomorphism is all about. So let's start with the definition. Two graphs are said to be isomorphic if there is a correspondence between the vertex sets of each graph. Remember, graphs are just are made up of sets of vertices and edges, right? So if we can come up with a correspondence between the two vertex sets of these two graphs such that there is an edge between two vertices of one graph, if and only if there is an edge between the corresponding vertices of the second graph. If we can come up with this correspondence, then we would say that the two graphs are isomorphic. So let's look at an example here. So we have two graphs, G and G prime. G has the vertices 1, 2, 3, 4, 5. G prime has A, B, C, D, E. What are the edges? We can find those by looking to see where the lines are. And the edges are listed there for G and here for G prime. So now if these are isomorphic, then we need to find some correspondence between the sets V and V prime such that when there's an edge between two vertices in V for the graph called G, there's also a corresponding, there's an edge between the corresponding vertices of the second graph. Okay, so let's come up with this function here. And so you're not going to have to really worry about how to come up with these correspondences. Maybe for a very easy example, you might need to do that, but don't worry about thinking that you have to be given two graphs and then come up with this correspondence yourself. It's just a matter of if we can find that, then we can say these are isomorphic. So this is one that's going to work. This is a correspondence that's going to work. That if we take these vertices from V, 1, 2, 3, 4, 5, and make this correspondence here, this function, we have the vertices in V prime, we'll say that, that these vertices in V prime are the function values, or this function f here. So 1, we're saying, corresponds to A, 2 corresponds to C, 3 to E, 4 to B, 5 to D, okay? If that's the case, we would want to check and see, if this is a correspondence, let's check and see, is that the correspondence, a correspondence, that would show to us that these two graphs are isomorphic. Okay, so let's go back up and look at the definition. If there's an edge between vertices of there's an edge between two vertices of one graph, if and only there's an edge between the corresponding vertices of the second graph. So let's look at graph G. We see that there's a line between 1 and 2, so there's an edge at 1, 2. So what does 1, 2 correspond to? Let's come over to the function. 1 corresponds to A, 2 corresponds to C. So there's a line between 1 and 2. Is there a line between A and C? Yes, there is. Okay, and we'd have to do that for every edge in G. So between 2 and 3, there is an edge. So 2 and 3 will go over to the function and see that's C and E. So is there a line, an edge between C and E? Yes, there is. Okay, and we would do that for all of those and find that yes, every edge in G, for every set of vertices in G that have an edge, those corresponding vertices in G prime also have an edge. So we would say, because we found this correspondence, that these two graphs are isomorphic. So let's now talk about the true, real definition of isomorphic graphs now that you've kind of seen how this works. Let's say that G is this graph. Again, we'll call it, we'll say that it is made up of the two sets V and E, the vertices and the edges, and then we have G prime that's made up of the V prime and E prime. Then, here's the definition. G and G prime are isomorphic if there is a bijection, we'll call F, that goes from the vertices from G to the vertices from G prime. And we're going to have some condition here, but let's first talk. Remember, a bijection is just a function that has a clear inverse, right? And we can see over in our example here that function does have a clear inverse, so we would call that a bijection. So these two graphs are isomorphic if there's a bijection such that for every pair of vertices x, y in V, then we see that the edge in E, is there if and only if there's an edge between those two corresponding vertices, right? F of x, f of y, those are just the corresponding vertices of x and y. And if there's an edge between x and y and E, then if these are really truly isomorphic, there's also an edge between the corresponding vertices. And it's an if and only if, so it would go back the other way too. If there's an edge in the corresponding vertices, then there must be an edge in the original graph G. Okay, so that is the official definition. And another word we might need to talk about is just the word isomorphism. We've already talked about what isomorphic means. So what is an actual isomorphism? So it's that correspondence, that function F is the isomorphism. Okay, so it's the actual correspondence that we say is the isomorphism. So our function here would be our isomorphism. Now notice, we could have come up with some other functions that if we had 1, 2, 3, 4, 5 correspond to just in alphabetical order A, B, C, D, E, we would not have found this this correspondence between the edges. So just because two graphs are isomorphic doesn't mean every correspondence is going to be an isomorphism. There's just some of them we might be able to find one, maybe we can't. So that's how that's what we can do with this. And as I said, don't worry, we're going to talk a lot about some other things here and find out how we might be able to say whether two graphs are isomorphic or not without having to try all of these correspondences to see if one will work. Okay, so the goal here is not that we're going to just be saying come up with an isomorphism. We're going to be learning how we can say that two graphs are either isomorphic or not without having to actually come up with that correspondence. Okay, well here let's just we're going to be given a function. We have 1, 2, 3, 4 vertices called 1, 2, 3, 4 and then A, B, C, D. And we're given this function. We're told f of 1 equals A, f of 2 equals B, f of 3 equals C, f of 4 equals D. Is this function from capital V, remember what's capital V, that's the set of vertices in G, to V prime, the set of vertices in G prime, is that function an isomorphism? Okay, well, we would just have to take a look and see. So let's just look, and here I'll go ahead and say what came up on the screen. 1, 3 is an edge in G. So let's look in G. There is a line between 1 and 3. But f of 1 and f of 3, that would be A and C. There's not an edge there. So, to find that, we would have had to just look one by one. We would have said, okay, I see a line between 1 and 2. Is there a line between A and B? Yes. And, just kind of go from there. But then we'd say, well, there's a line between 1 and 3 in G. Is there a line between A and C in G? No, there's not. So that's how we would have found that. And so then we could say that F is not an isomorphism from G to G prime, because we found that particular correspondence is not an isomorphism. Now, it doesn't mean that we can't find another correspondence that would work, right? That's not what we're saying. We're just saying that this particular correspondence, F, is not an isomorphism from G to G prime. How about this function here? Is this G, we're going to call this function G, and we have this correspondence where 1 corresponds to D, 2 corresponds to A, 3 to B, 4 to C. Well, we would just again have to just kind of go through all of these different edges and check. If it's in G, then there needs to be a corresponding edge in G prime. So let's just start with the edge 1, 3. 1, 3 is an edge in G. So we've got to see what corresponds to 1 and 3. So looking at that G, those G values, 1 and 3 corresponds to D and B. So we would need to ask ourselves, is there a line between D and B? And we would find, yes, there is. Okay. What are some other edges in G? 1, 2. That's an edge in G. 1 and 2 correspond to D and A. Is there a line between D and A? Yes. Okay. 2 and 3 is an edge in G. That corresponds to A and B. Is there a line between A and B? Yes. And we could keep going and find that, yeah, every edge in G has a corresponding edge in G prime if we use that correspondence. So we would then be able to say, since every edge in V has also has a corresponding edge in V prime, then we would say that that this function called G is an isomorphism from G to G prime. Okay, so again, it's the function itself that's the isomorphism, but we would be able to, once we find this isomorphism, we can say that the two graphs are isomorphic. Now, a property, this might be the number of vertices, it might be the number of total degree, all kinds of different properties that you might imagine having to do with graphs. A property is said to be preserved under isomorphism if whenever two graphs are isomorphic, one graph has the property if and only if the other graph has the property. So if if a property is preserved under isomorphism and we find that one graph has the property and another graph doesn't have the property, then we can say that those two graphs are not isomorphic. So we're going to be learning about some different properties that are preserved under isomorphism. The first one is vertex degree. This theorem says that vertex degree is preserved under isomorphism. Consider two graphs G and G prime. Let F be an isomorphism from G to G prime. For each vertex V and G, the degree of vertex V and G is equal to the degree of vertex F of V in G prime. Okay, so basically, if it's a corresponding vertex, then it's got the same degree. So here's two graphs here, and we see that there is, this was the correspondence that we found. And if we take a look at the first graph, actually we can just, make it a little easier here and just make the observation that each vertex in the first graph has a degree of 2. And then we can look over on the second graph and see each vertex also has a degree of 2. So we know that, each vertex one would correspond with A. Those both have a degree of 2. 2 corresponds with C. Those both have a degree of 2. So we see that it is true in this case that the vertex degree, the degree between two corresponding vertices, will always be the same if we have found an isomorphism. Okay. Now, if I were asked whether these two graphs are isomorphic, as I said, originally with the definition, you might think that, well, the only way to say no is to try all of the possibilities to see if any kind of correspondence would give us what we're looking for as far as corresponding edges go, right? But now that we know this theorem that says that vertex degree is preserved under isomorphism, then we could look at these two graphs and say, you know what? There does not exist a correspondence that would make these two graphs that would show that these two graphs are isomorphic. And why is that? Well, let's look at every vertex in the first one, again, has a degree of 2. But look at A in the second one. It has a degree of 3, and so does C. And there's no corresponding vertex that we could correspond. We couldn't correspond something from the first to A or to C because, we could make that correspondence, but we would see that the correspondence has, in one case there's 2, the degree is 2, in the other case the degree is 3. So we would say that because we know that the vertex degree is preserved under isomorphism, we would say there is no way that we will be able to find an isomorphism for these two graphs. Okay, so in the second graph, A and C have degree 3. They would have to correspond to vertices in the first graph with degree 3, but there are none available since each vertex has a degree 2. So we could rule out any question about whether these two are isomorphic. We could say no, they're not. And we have some other properties that are also preserved under isomorphism: number of vertices and number of edges. So if two graphs have a different number of vertices or edges, then we also know that they can't be isomorphic based upon this statement that we've just heard. You would probably guess that. You would have guessed that if I had asked, do you think these are preserved under isomorphism? And it would be pretty easy to think that through and say, absolutely yes. But anyway, we're given that now, and we can just use that directly. Again, we don't have to try to come up with a bunch of correspondences to try to find an isomorphism if it's not going to be there. If we can rule out the fact that they're isomorphic to begin with. So here's two graphs. It has one graph has 5 vertices, the other one has 4. So, if we thought through the definition of isomorphism, we could say there's no way we can find this correspondence because we can't come up with a bijection because we can't have a clear, inverse and so on. So anyway, we could think through that, but we could also just take this statement as the truth, which it is, and we can just use that and say, well, there's 5 vertices in one graph, 4 in the other. So, and I know that if two graphs are isomorphic, they would have the same number of vertices. So we could say right off that those are not isomorphic because they have a different number of vertices. Over here, there's the same number of vertices, but we could count the edges and say that there's a different number of edges in each of these. And that was another thing up there. We said the number of vertices and number of edges in a graph are properties preserved under isomorphism. So we would say that, again, from that we would say, no, these two graphs cannot be isomorphic. They have a different number of edges. Okay, so if I gave you two graphs here, you might need to be able to tell me if you can rule out the fact, rule out that they're isomorphic. And so what we might do, that one of the easiest things to do, is just start counting vertices first, and if they're the same, then start counting edges. So looks like they have the same number of vertices, but it looks like there's one extra edge in the second graph. So that's one way. So not having the same number of edges is one way you could say that they're not isomorphic. But there's another way too, besides counting edges. We could look at the first graph and say that there are two vertices in the first graph that have only a degree of 2. But in the second graph, all of the vertices have a degree, greater than 2. So there's no corresponding vertex with that same degree. So either of those either of those observations would be enough for us to rule out that they are isomorphic. So either of those observations are sufficient to show that the two graphs are not isomorphic. Okay, let's look at this. Well, one of the easiest ones here is just to see that they don't have the same number of vertices. So that's one. But another one, you could say that in the second graph, D and B have a degree of 3. And there are no vertices in the first graph that have a degree of 3. And we know that the degree of corresponding vertices is preserved under isomorphism, and so that would be another reason why we could say that it's not isomorphic. So either of those observations would be sufficient to show that the two graphs are not isomorphic. Here's another one. And again, we could start counting vertices. That's okay. We could start counting edges, and those are okay, right? Because it looks like we have the same number of edges in each one, but we might want to look at that vertex called C over there on the right. It has a degree of 2. There's only one of those vertices in that second graph that has a degree of 2. But let's go over to the first graph. We see a 5 and a 2 have a degree of 2. So there's 2 vertices in the first graph that have a degree of 2, but only one vertex in the second graph that has a degree of 2. And so that then would tell us that we could use that fact to say that those two were not isomorphic. Okay, here's a new definition, but that's going to kind of help us also in give us another way to be able to tell quickly whether two graphs are isomorphic or not. Remember, when the graphs are small like they are here and pretty simple, it's pretty easy to just check real quick how many degrees are there in each vertex, and count count them and all that. But when it gets a little bit more complicated, it might be a little bit harder. So using what's called a degree sequence might also be able to help us. So a degree sequence of a graph is a list of the degrees of all of the vertices in non-increasing order. So you just take all the vertices, find their degrees, and list them in non-increasing order. So that means you're never going to get bigger as you go through the list. You start with the highest number of degrees and go down. So here with this this graph G, we'll look at all the degrees. So vertex 1 has degree of 4, 2 has a degree of 2, and so on. So those are the degrees of each of those vertices. Now the degree sequence is pretty simple. It's just taking all of those and putting them in non-increasing order. So the largest first going on down. So 4, 3, 3, 2, 2. That would be the degree sequence of G. Over here we have G prime. Let's look at the degrees of each of those. If we did that, this is what we would find. We'd find all of those different degrees. So the degree sequence of G prime then would be, again, non-increasing orders. So start with the biggest, 3, 3, 3, 3, and 2. Now, as you might have guessed, degree sequence is another property that's preserved under isomorphism. So if two graphs have a different degree sequence, then we know that there's no way that they're isomorphic. Okay? So in all of these, just note that we're using these properties to rule out isomorphism. We can't use the properties to say that they are isomorphic, right? So like I can't just take two graphs with the same number of vertices and say I know they're isomorphic because they have the same number of vertices. No, that's not enough. It's just that each of these properties we're talking about are enough to rule it out, but it's not enough to prove that there is an isomorphism. But anyway, in this case here, we see that the degree sequence is preserved. So I see that I have two different degree sequences, and so I would know that these cannot be isomorphic.